So what if you were assigned number 15 and 16, which turns out not to be a hypothetical question, where you have these weird functions and they might be hard to integrate, but look what the direction says. It says find the average value of the function without integrating by appealing to the geometry. So what I like about these is what they could do to you on the AP exam. They could ask you the average value of this function, right? The key word here is find the average value of the function on this specific interval. They wouldn't have to give you the function in either case. As long as we have the graph, we can do the integral easily without even having to do the integral, as it says, without integrating. So let's go ahead and follow the book directions on that one. So here's number 15, and I just have this graph here. So how am I going to find the average value? Well, I know that the average value is equal, that says V with a subscript AVE, average, in case it's not clear, V average value, is 1 over b minus a times the integral from a to b of f of x dx. So what's b minus a? It's 2 minus negative 4. So that's 1 over, I'll go ahead and write 2 minus negative 4, I don't mind doing that, times the integral from negative 4 to 2, because the lower number goes in the bottom, of f of x dx. Well, how would I do the integral if I didn't even have the function? Or if it's some weird piecewise function, or square root of an x squared, and I don't know how to do that. All right. I have the graph, I can get the integral from the area. So sometimes you use integrals to find the areas, but sometimes you use the area to find the integral. And I believe I've mentioned before on AP exam questions, a lot of times if the graph consists of line segments, or semicircles, they often want you to find the area geometrically and then use that to make a conclusion about the integral. So all you have to do is find this area, and that's going to be equal to this integral. So then my 1 over 2 minus negative 4, of course, is 1/6, and this is just the area of the triangle, right? The area of the triangle, which this is a triangle with base 6, and the height is 3, so that is 1/2 times 6 times 3. So then, what can I do? Cancel the 6's, and I get 3 over 2. That's the average value of that function, 3 over 2. On average, this is the function, it stays at an average of 1.5. For this nice linear function, that seems kind of obvious, all right? But for this function that you're going to have to use, you do using the area of a circle and the area of a rectangle and subtracting them, hint, all right? It's not going to be obvious what the average value is. Like, what do you think the average value might be? Do you think it's going to be lower than the middle, or do you think it's going to be, right, the exact middle would be 1/2. Do you think the average value is going to be exactly 1/2, or do you think it's going to be higher than 1/2? Or do you think it's going to be less than 1/2? You will get to find out, because that one's assigned as homework. All right, next up is Fundamental Theorem of Calculus Part 1. So again, with the proviso that Part 1 and Part 2 are arbitrary designations, here's how we in the College Board world describe the parts of the fundamental theorem. Part 1 says the derivative of the integral is equal to the original function. So this was the first one we derived, that's why we call it Part 1, and it essentially says that the integral and the derivative undo each other. If I do the derivative of the integral, I get the original function back. Some key features of this: the a does not matter. We talked about y in earlier discussions. Maybe we'll talk about it again. But essentially, it's that if you think about this integral, right? This integral would be capital F of x minus capital F of a, and then I would do the derivative of that. Capital F of x is a function, but capital F of a would be a constant, and the derivative would go away and be 0. So this a at the bottom does not matter. There are also geometric reasons why it doesn't matter. All right, so it doesn't matter what that, it could be a billion, it could be negative 36 pi over e to the 57th, does not matter. All right, other things that are important. This variable matches this variable, but not this variable, which matches this variable. So these two variables match, these two variables match, these two variables are different, and that's important. And then when you do get a function value, it matches this derivative. Oh, I used the wrong color. I tried to be color coordinated and I failed. Okay, so x, 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 t, t. A doesn't matter. All right, we're going to work a lot with this one. This is what we're going to talk about today. Now, just by comparison, part 2 says the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F prime is equal to f. So, I mean, in a certain way, it's saying the same thing. This is saying that if I do the integral of the derivative of a function, I get the function value back. This is saying the integral of the derivative. This is saying if I do the derivative of the integral, I get the original function back. So what the two parts of the fundamental theorem of calculus essentially say is that integral and derivative undo each other. So we mentioned before, I mentioned once before, we can call them inverses in a certain way. So if you think inverse functions, f of f inverse equals x. Right? F of f inverse of x equals x. F inverse of f of x equals x. That's another important property of the inverses. The square root of x squared is x. All right, it's really absolute value of x, but that's because x squared is not really a one-to-one function. The cube root of x cubed is x. All right, the inverse sine of the sine of x is x, subject to the domain restriction. All right, so what inverse means is that one of them undoes the other. So this essentially says the derivative of the integral is the function. This essentially says the integral of the derivative is the function. All right, now there's a fancy word for functions whose domain and range are also functions. Like, you could think of it that way. You could think of derivative as being a function where derivative of f of x equals f prime of x. So you could think of derivative as a set of ordered pairs, f of x, f prime of x. This is a little bit theoretical, a little out there, you don't need this, but it's fun to think about for me. The set of functions f of x, f prime of x, such that f prime of x is the derivative of f of x. All right, so but this is a function. It's a set of ordered pairs. It is a function, but it's a function whose domain and range are the set of all real valued functions. That has a name. A function of functions is called an operator. So both derivative and integral are considered operators. The integral and derivative are inverse operators. Okay, so this is all very theoretical. This is a little bit more concrete. We're going to talk about what you're actually exactly going to do with it next.